Ah, lui si mette la cosa. Cominciamo?
È il puntatore? Se vuoi usare il puntatore.
È a posto col puntatore, tutto a posto. Ok.
Serve qualcosa?
No, cercava il suo puntatore. Possiamo cominciare? Ah, beh, perché inizi tu, certo. Comincio. Bene, benvenuti a tutti.
Good morning, welcome. This meeting has not been scheduled. When the agenda of this year meeting was finalized at the beginning of July, this meeting had not been included in it. But the morning of the 4th of July, at the CERN of Geneva, a very important announcement was made. A Higgs boson had been described, and that afternoon there was a meeting of the organizing committee where learned about this announcement, and so unanimously we decided to include this meeting by changing the agenda. That is a clear sign of the interest and the importance of this subject. This also bears witness of the attention and sensitivity that the meeting has always devoted to novelties, to new discoveries in all fields of knowledge. All the more so in the field of scientific knowledge, which presents us with different scenarios which we cannot plan. It is those which are presented by nature and which we come to appreciate thanks to the study and work as well as the passion of many people working together in a team and allow us to see something new. We are really enthusiastic of this because everything which concerns beauty and truth makes us happy and enthusiastic. We are here to talk about an extremely important discovery for physics and science. I would say that when nearly 30 years ago, researchers at CERN were beginning to think of LHC, the machine which will be described this morning. Well, they had thought to be able to appreciate the existence of this particle, i.e. Higgs boson. When we say to see the particle, well, the verb to see is used metaphorically because there is a lot of sophistication when we say to see something in physics. And this natural sense, this ability to see, has been very much widened to give evidence of the boson. We have two distinguished experts today who will speak about this discovery, which at the center has one of the key questions of Greek philosophy, which in terms of modern physics is stated and reformulated. So what are the constituent elements of matter? And in particular, what is the mass of a particle, as if it were the mass of our body or another common object? What's the nature of this property, which is the one which makes us able to perceive the weight of objects or their resisting to impulses? This is the subject of today. Let me introduce our guests. This meeting has organized at the very last minute. That was a very last-minute invitation for the guests, in particular for Sergio Bertolucci, whom I will introduce. And thank you for being here.
Sergio è arrivato ieri sera alle 10.
Sergio got here yesterday night from Moscow, and he did, you know, a triple jump to be here today. Sergio is the director of the Research and Scientific Computing Department at CERN. He is the point of reference of the whole project, which is an extraordinary one. It's a great thing at CERN. He studied physics at the University of Pisa in Italy. He worked in the field of particle physics in experimental terms at DESI in Hamburg, at Fermilan in Chicago, and at the Frascati lab of INFN. He was a key director in the building and use of accelerators, CDF, KLOI, and Daphne Collider, and other experiments. Among the most important achievements is the discovery of the top quark. It has co-authored more than 370 works on scientific journals, and his H index is 82, which is really a top thing. It's a huge thing, like the top quark. He was the director at Frascati, deputy chairman at the INFN, and he worked mainly at CERN. He was the chairperson of the LHC committee from 2004 to 2007. He was part of the research board of CERN and the strategic scientific committee. And he's at present the director at the scientific computing unit at CERN. Lucio Rossi, thank you very much for being here. He's another protagonist of this discovery, which has a very important Italian component. He studied physics at Milan. At the beginning of the 80s, he built one of the first accelerators in the world, a superconductor. In 1989, starts collaborating at CERN to develop the first prototypes of LHC magnets. In 1997, he is collaborating with an Atlas centered in Geneva. In 2001, he leaves Milan University, though he remains a retired professor, and moves at CERN to the guide the magnet and superconductor group. He directed the building of 2,000 superconductor magnets. You'll see the picture, the real backbone of this wonderful machine, with a budget of 1,200 million euro, i.e. 1.2 billion, 50% of the whole budget of LHC. In 2011, he was appointed in charge of high luminosity LHC, which is the future version that in 2020, hopefully, will increase by 10 the efficacy of LHC. In 2007, he received the award IEEE for Korea for the contribution to applied superconductivity, which is indeed very important to have trained a full generation of leaders in the field. This is the motivation of the award.
Bene, non mi resta che dare...
Well, now the floor to Lucio, without further ado, who will start the event by speaking about LHC and his experience. Thank you very much. Thank you very much, my dear friend Bersanelli and organizers of the meeting, for inviting me again. This came quite unexpected. It's a great honor to be here, with my boss, Professor Bertolucci, to speak about the equipment. He indeed would have been the perfect person to speak of that. I deal with equipment. I'm not the person discovering. I am the person using the screwdrivers. But in order to see beyond, to appreciate what matter is, this fascinating subject, the more we progress, the more we find mysteries. The more we get to know, the more we appreciate that there are things to be elucidated. To do that, we should start with an equipment, starting from Galileo. 400 years ago, Galileo made something fundamental that was the beginning of modern science. He was a theoretical physicist, maybe the best in the world, but he made lots of experiments. He invented a tool, took what was a sort of a toy in the Netherlands, adding lenses and making it a scientific instrument. Some said that the telescope was invented in the Netherlands. This is not true, because the one who invented it was Galileo. And then he used that not for enjoyment or entertainment, but to extend the self, to go beyond and to follow the call of beauty, which generates astonishment. 400 years ago, Galileo invented the telescope. Let's move and go 101 years ago. Last year, the exhibition was devoted to Rutherford Geiger. Rutherford, 100 years ago, he made something special. He started using matter as a tool to investigate. In other words, he took atomic particles and used them to bomb the atom. And he was the first to learn about the nucleus in the atom, as we saw in the wonderful exhibition last year. 100 years ago, another important event happened, i.e. Omnis, a Dutch scientist, discovered superconductivity. So that was who was a scientist who for 12 years did not publish an article. Instead, he created a school made of people and engineers who worked at Leiden in the Netherlands for 80 years to manufacture the wonderful instruments he used to obtain an unexpected result, i.e. he discovered superconductivity. These are the two antigones, the fathers of LHC. Let's move to the 70s. Why LHC? At the CERN, in the 70s, an experiment was made. That wonderful trace, at that time, particles were seen like that, only a trace in a bubble chamber. The trace confirms, or is a clue, that something exists. Seeing does not mean seeing particles literally. We just see a number of clues which can lead us to a discovery. This is not seen directly, it's a form of indirect knowledge, but we can be positive that something is there, even if not directly seen. So by means of these traces, we realized that the boson could exist. Bosons are particles which like to work together. They are not single particles, and that was a clue. So we wondered, how can we see them? At the CERN, we had a wonderful accelerator, 7 kilometers long. It's the ABS super proto-synchrotron. That was not enough. So here the genius intervened, the person who sees things that others cannot see, Professor Rubbia. His engineer, Mr. Van der Meer, succeeded in finding the key. So the CERN became a factory of anti-protons, anti-matter. We create antimatter, which is also used in the hospitals nowadays, and they were able to use the old machine in a new way and were able to see the bosons WEZ. That's an acronym, and that awarded the Nobel Prize the year after. As usual, when you solve a problem, you create another one. We realized that because of the existence of bosons, there would have been another particle which might explain symmetry. We know that in nature there are symmetry laws. Nature is based on symmetry laws, but we had no tool to see that, so we had to invent something. The USA proposed to create an accelerator, the red circle. That's the city of Dallas, you know, it's a big city. An accelerator 86 kilometers long. The price would have been $15 billion. And CERN and Rubbia, who had become the general director of Rubbia, was, no, we already had an accelerator for electrons and anti-electrons, LEP, 27 kilometers long. So Rubbia and co-workers transformed it in a proton accelerator. So 27 kilometers is much less than 86. However, it could indeed be a good rival to the American one because it used better technologies. Rubbia and the CERN decided to work based on technology advance. Note the circle in the second picture, which is huge, but still smaller than the American one. So new technologies and a higher luminosity used, and I'll tell you what it is, i.e. more light to see better. Why are we doing this? Accelerators are at one extreme of the scale of knowledge. This is the universe in centimeters. To the extremes, to the end, we see the larger things, the whole universe. To see that, we need space telescopes. The latest is Planck. These are the telescopes to see what is infinitely big. But if we want to see the infinitely little molecules, atoms, nucleus, electrons, the nucleus is made of protons and neutrons, and into the nucleus we have the quarks. And the quarks are here in the scale approximately. The accelerator is an object which are extremely little. I'm not explaining you the formula there. 1/10000000th of meter can be seen. You know nanotechnologies. Why can we speak about nanotechnologies? Because we have the nanoscopes which can visualize atoms and molecules because they have the size of a nanometer. The accelerator is a nanoscope seeing 1/10000000th of the nanoscope, so we can really see what's inside the quarks. In doing that, LHC, we say, replicates the Big Bang, but it's far away from that. Anyway, we are working to that. So while going to the infinitely little, as astrophysics do, we go backward in time. So the formula, if you understand that, illustrates how much we can go back in time. And in LHC, we put the values called TeV, and with the collisions, we can see 1 picosecond. For other phenomena, 1 microsecond after the Big Bang. The universe is 13 billion years old, and we can go back to an infinitely short time after the Big Bang. So we see elementary particles. Still, it's very difficult how to explain the complexity of the world and of life. So that's indeed a much more difficult discipline. So what do we do? What are the tools we use? We take the particles, we concentrate them with energy, opposite to what an energy station does. We take the particles, we load them with energy, i.e. mass, and we have them collide. While colliding is like putting a little car in the accelerator. We accelerate, and the limit acceleration is the speed of light. We don't reach that speed, but we go very close to that. How can we accelerate? Again, that increases the mass. If we give energy, as Einstein said, the mass increases. In doing that, the little car there becomes like a big truck. It's full of energy, so we need big magnets to have it bend, because we need more centripetal force to have a big truck make a bend. While colliding, some parts come away which are much heavier than initial particle. This is what accelerators do. This is their secret. So they generate a sort of light which is so thin that I can see the infinitely little. You know that the essential light is essential to see. We can see anything in the dark, but light is not enough. We need a person seeing. So detectors are very important, detecting the particles generated. So we need light to see. We need to see the eye watching and the brain processing. But Professor Bertolucci will expand on that. So all these objects need to have leading technologies. Let us see how accelerators work. This is the chain of accelerators at CERN. PS, this object has about 60 years. We use it again. We use what our fathers gave us. We use it as long as we can, and that was the winning card. So to go beyond in the research, we use tradition. So particles are generated in the LINAC machine, which is short, about 25 meters, and then it goes into a number of larger rings, and this is the SPS, Nobel Prize Robia, and then they are put in the LHC and they collide. This is Peter Higgs, the Scottish scientist. Now Professor Bertolucci will present the theories by Peter Higgs. That project lasted more than 20 years for the building, but since its conception, 30 years have elapsed. I am at the CERN because in 1989 we started collaborating with that institute with the first prototypes. This is the key prototype. Note the INFN acronym. That is the institute in Milan producing it together with CERN, and that was the first magnet prototype of LHC. CERN, 6 months later, approved the first project in '94. But from the prototype till the end, 14 years elapsed. It was a long way. It was like building a cathedral. We had to develop new technologies, and the first is superconductivity. We can have magnets which can bend the particles which have a lot of mass, like the big trucks I mentioned before. We had to develop materials like this, for example, this wire, which is the superconducting wire, is made of many wires of 1 millimeter. If you just peel a wire or a cable, you'll see very thin yarns. But indeed, 10 amperes are the plugs at home. In our wires, we have 1,000 amperes. If combined, they can have 15, 20,000 amperes. But they never get hot, so energy is not dissipated. This is the advantage of superconductivity. You see these very thin filaments. In 1 millimeter, we have 6,000 filaments not touching. If these filaments were put one after the other, they will be about 1 billion kilometers, 6 times the distance between the Earth and the Sun return. And this was the first technology. Then we have superfluidity, another important technology. We had to develop the super cold. Just think that in order to work, such magnets should be at a very low temperature, about 1.9 degrees above the absolute zero, which is minus 271 degrees Celsius. So out of 40,000 tons, well, we can appreciate 40,000 tons. The degree of temperature which the universe will achieve in 10,000 years. So that is there to produce the superfluid helium. So that is the machine, is a cartoon. That's a wonderful equipment. I went to CERN for passion, not only for money. I'm very much attracted by beautiful technologies. This is the superconducting dipole of LHC with a number of coils which are superconducting with particles. The yellow lines are the bundles of particles entering the collider into two opposite directions, and they travel at the speed of light. And in only 4 points, with special magnets, we have them cross and collide. And this is the machine with the magnets. It's 27 kilometers of magnets. It's like the arches of a Romanic cathedral. They are very repetitive, but still they are very beautiful. These blue tubes are the symbol of LHC, but creating lights is not enough. And this is the largest eye. This is one of the most beautiful pictures of LHC. I worked in studying these arms, which are the magnetic arms of the Atlas detector. It's immense. It's like a cathedral. This is another detector. CMS is name of this. These are the most important who saw Higgs boson. These eyes are full of electronics. They can uptake the images in this hullabaloo. I mean, if you are able to identify a trace, this is just a drawing. You'll see the real picture. We expect one Higgs boson out of 1,000 billion events. So to see, we have 20 million collisions per second. So these detectors are like photo cameras taking millions of pictures per second. 20 at present, 40 million per second in some time. So they are very active. With LHC, well, in 2008, Google published this picture, 10th of September 2008. That day, Google logos was that. It was like a prophecy. That seemed to be an explosion, which in fact it happened 9 days later. That is the superconducting wire. There was a fault in the connection between magnets and superconductor wires, and they weigh 30 tons each, more than a truck. So 700 meters of magnets pushed one against the other because of helium pressure and overheating. 14 months we stopped, then we resumed, and we worked a lot. We had a number of teams. We had to recreate the teams. It was difficult to motivate people again, but everyone was willing to work and to have a common objectives for something bigger. That helps us going beyond the feeling of guilt, those who thought they had made a mistake, and so on. Anyway, on the 23rd of November 2009, memorable date, the two bundles are there. Well, the green line is the bundle of particles going around the 27 kilometers. In terms of height, it oscillates less than 2 millimeters. That was the first bundle we shot. It was so perfect that it just oscillated 2 or 3 millimeters in height by doing the first turn. That was great. That demonstrated that the machine could work and bear the expected results. As Professor Bertolucci will tell you, Higgs is there. But we will find much more. When we enter a room and see something, we usually want to see better. To do that, we increase the light. And this is what we want to do, as we said at the beginning. We would like to have a high luminosity LHC to increase the quantity of light and see better, and to increase the number of collisions. To give you an idea, last year we generated 500,000 billion events. This year, 600,000 billion at a higher TeV, which is a high density. So we saw the Higgs boson. By 2020, we'll be able to generate 30 million billion of events so that we can quantify it. But that is not enough. because we know that we want to do something more. There is something which pushes us to go beyond. With the high luminosity project, we hope to achieve 300 million billions of events. This chart illustrates what we did. We started in '75 with a Tivatron in the US and SPS. The high luminosity LHC, we will arrive at that level of central field. We would like to make a quantum leap to reach a more powerful LHC, following our wish to go beyond. In doing this, and then we are attracted, we are doing a journey which has special effects. For example, the web. Many might not know that it was invented in the CERN 1989. The inventor was Tim Berners-Lee. And then the grid is the future web, the medical applications. You know what a PET scan is. P stands for positron, the antimatter. Antimatter does exist. It can be controlled and is used for beneficial purposes. This is the first PET on the brain of a rat taken at CERN in 1975. And then it is used to obtain pictures like this. This is combining with another technology, the skeleton of a rat with the details. Just look at the picture on the right and the evolution which has happened. Just think, Pavia, not far away from here, we have the National Center for Oncology Hydrotherapy. The machine is smaller than LHC. Still, it accelerates particles to treat tumors directly on the patient. It's a reality. The ring is being there with the first medical clinical protocols, and Italy is really in the van. Not many know that magnetic resonance is made of a superconducting magnet. Magnets were developed thanks to Tivatron and LHC, because we developed the basic element, i.e. superconductivity. This patient is not aware that it's 2 centimeters away from cosmic cold. And finally, another application, another hint of what can be done. This is a project supported by Professor Rubbia. You know, he's brilliant. And also by other groups in Germany to offer renewable energy. Where is solar energy? Well, in the Sahara. Professor Rubbia found a way to have a solar energy producing station also at night with a 15 gigawatt power station. But if I do that, I have to convey energy throughout Europe. So to transport energy, well, this is something complex because such electric power to be transported would need cables, and I'm sure that nobody in Italy would accept to have an aerial line like that. So the idea is to use superconductors we are developing to have superconducting cables which can convey such energy. So note what comes from that research, which still continues. As a technologist, I would like to remind you that if we don't enhance this primeval element of research, we'll never able to find technologies. Those who look for technologies for the sake of technology, they will lose it. Thank you very much for your attention.
Grazie, Lucio, grande. guardi da qua, aspetta. Ah, ti metti là, perfetto. Vai pure, è tua. Vai, vai.
Bene, avete visto tutto.
Good morning. I mean, Lucio told the whole story. Instruments like that, we really enjoy ourselves very much. We are a very united community. Lucio was making a joke when he said that he's the one using the screwdrivers and the mines come later. But we work all together. We indeed are specialized in different fields. That's it. So when it comes to present my paper, I'd like to describe the CERN. CERN is indeed our lab. It's partly Italian because it's an European lab. That is the mission, the triangle of knowledge. At the basics, we have the basic mission, push forward the frontiers of knowledge of the physical world. We want to better understand why the universe is like it is and how it evolved, what was its growth and its possible future from the point of view of physics. These are important supreme questions which appear to be immaterial. As a matter of fact, since language was invented and human beings started reflecting on the world, that had always provoked changes and generated what we call progress. To answer such questions, we need to develop new technologies, as Lucio told you, for two reasons. Either because the technology we need is not there, or maybe it's there, but it's too expensive. So that has an immediate benefit for the society. For the things that we develop can translate in applications in other fields. For example, the web. Here we have a lot of young people. I'm sure that the majority of you could think that after the discovery of the Americas, the web was invented. In 1988, the web was not there. We had networks. Networks such as the Internet was used to shift information from one point to the other, but very rigidly. In 1989, this gentleman, who is a Baron of the Queen, Sir Tim Berners-Lee, went to his boss and said, I have an idea to improve communication in our experiment, which was huge at that time. And luckily, his boss said, your idea is promising, though a bit confused. You have the go-ahead. And so he wrote in a universal language which changed the way in which he used the network. Each node can use and generate information at the same time in a global way. When you write HTTP, etc., you use the markup language invented by Mosaic, the first browser, and that really changed the world. Today, 1/3 of the world economy rotates around the web. CERN could have patented that, but that is not the mission. We want to do research for everyone, so the CERN decided not to patent the web. They rather kept the intellectual property. In that way, nobody will ask you to pay something to write HTTP and so on and so forth. Well, I mean, they have other more creative systems to make you pay. Anyway, another side of triangle is that research needs ideas and funds, but it mainly needs virgin eyes. The people who make the difference are, it's the brain of young persons. The elderly brains, like mine, maybe are much more knowledgeable. Well, this is not my case anyway. The more I grow, the more ignorant I am. In general, we get used to accept that certain things with which we are born are true. So we need, every now and then, to have someone challenging that, a person looking at the same thing for 20 years and who could tell us, well, no, this is completely different. So it's key in this field to have new generations involved constantly. The CERN is a place to train scientists, engineers, IT experts, and we train hundreds of them every year. We are a privileged place because we come before the interest of nations in economic terms. Science has advantages because unites people beyond religions and ideologies. We are one of the only languages of peace. There are more than 100 nationalities working together. And there are not many examples where you see an Iranian working with an American, a Palestinian, an Israeli, an Italian with other Italians. So from this point of view, we are a special community. Our mission is that of going on to make progress, hoping that the progress is such to generate discontinuity, because the real discoveries are not made when you progress along the same path, which is good for science, but the real revolutions are made when a gap, a discontinuity is created. It's a difference between research and technology. Indeed, if you are able to make candles and the society says, well, the best thing is to make candles, you will continually improve the candles, will never be able to make an electric bulbs. But there is something in between, such as, for example, Maxwell equation. And if you don't master Maxwell equation, you'll never invent electric bulb. Just think of your mobile, which is made with a thermoionic valves. It would be much bigger than this hall. It would consume megawatts, many megawatts, and it would not be very practical. It will not stay in your pocket. The thermoionic valve, the transistor, the integrated circuit, and so on, there are millions of transistors in your phone, and what stands in between is quantum mechanics. When the first time quantum mechanics was said, everybody was astonished. Let's look at the antimatter. It's not only there to have Angels and Demons movie made. In 1929, when the equation was written, he had two solutions, two possibilities. One, I'm a fool, that's wrong, or that's an electron going back into time. 1929, the antiparticle of an electron. Well, they didn't know that he could be used to make diagnosis of cancer. CERN is one of the brilliant ideas of Europeans. After the Second World War, Europe was shattered by the war because of self-destruction. A group of scientists among which Edoardo Nardi thought that the best way to unite Europe again was to use science. That happened after the war. It was not easy to convene around the same table Germans, Brits, Italians, French, and so on, who had fought till a few years before trying to destroy the others. In 1954, CERN was founded under the auspices of UNESCO. There are now more than 20 member states. A few years ago, we also were able, through the Council, which is the governing body in terms of guidance, stated that to be a member of the CERN, it's not necessary to be European. So now we have many other nations, Israel, and Brazil and Russia entering, India, and they will be members of the CERN. So we are sort of global institution. The nice thing of CERN is that to make research, it's not necessary to be a citizen of the member state, not to be a state. So we have about 3,000 people as staff, but we also have a community of 11,000 physicists as users. 830 million euro per year is the budget. So investing 830 million globally was a good investment and still is. This is the distribution of all CERN users by nationality. Unfortunately, there are white areas because they have more urgent problems than discovering Higgs boson. And we hope we could cover the white areas soon, because that will mean that we will be a huge force together. So this is what we are doing. We know that the universe was created approximately 14 billion years ago, after the Big Bang. The idea of a bang is nice to say, but it's not really accurate. But when an explosion, a bang happens, that means that there is something expanding in a time and space which is already there. As a matter of fact, the bang, when happening, it created the space and the time where it was taking place. A good analogy is that of being on a surface of a balloon which is being inflated. At any point of the balloon, if reasonably round, you see all the things around you getting distant and distant, and this more distant. And this is the idea of a space which is being created and a time created when the expansion was started. If we want to study the universe, which is now a size of 10 to the power of 28 centimeters, Lucio said, unfortunately, the parameter is centimeters. Physicists like to use centimeters, which is not a standard. An engineer, that is pure blasphemy, because they use meters. But we say that we use 28. 10 to the power of 28 is easy to remember because it's just a square of the public debt of the USA. So it's much easier to be kept by mind. Here we have two possibilities to understand the universe. Just try and see how it was when it was young, because the symmetries were easier to see because there was not so much time to differentiate. So going in that section of time, it makes it easier to understand how it is. Looking at very distant objects is good. Information is conveyed at the speed of light. The galaxy, with 1 billion light years, you are just looking at the universe as it was 1 billion years ago. And we are getting increasingly accurate in doing that. This approach has one limit, because if you look far, far in the distance, going backward in time, you reach a point when there is a sort of wall there, and the wall is at 250,000 years after the Big Bang. Why is that wall there? Because the universe was so hot that all the information emitted, i.e. the light which was emitted, it was reabsorbed. So there is some confusion. That is very promising, because if we could study that wall, we would be able to appreciate what had happened before, and what our colleague Marco is doing together with Remo Mandolesi sitting there. They are the people who are behind the Planck satellite project, but they are studying that moment in time. From the fluctuations, or the way in which you approach the echo of the Big Bang at the interface indicated in green, you'll be able to appreciate how the universe was before. There is another way. This is the ruler that Lucio showed you before. It is a log ruler. Every line is a factor by 10. So that is the size of the universe. This is power 10 to the power of minus 32. It's the smallest size we can conceive on the Planck scale. The size of the fluctuation of the void. There is nothing fuller than void, but would deserve a seminar of 1 hour. Maybe I come next year to tell you. So this ruler at the center, well, we have been very sly, sorry, because this is the moment of man. Here we have Marco. So if we go back in time, we can watch in the distance, and the best instrument to do that is a Planck telescope, or we go beyond the wall by creating a very little space for a very limited time to recreate the conditions near to the Big Bang. The more energy we put there, the length of that event is 1/1000th of billionth of billionth of a second, the more we approach the beginning of the universe. With LHC, we are able to watch the universe how it was 1/1000th of 1/1000th of millionth of a second after the Big Bang. You might not believe it, but the large majority of interesting things happened before. We do that, otherwise we will be jobless. Anyway, we will continue. It is key that today we understand that the next evolution of a theory of physics will have to be supported. We'll have to understand what is extremely little and what is extremely big. We know that today we cannot give a good answer simply by looking at one of the two ends of the scale. If we were satisfied easily, we would have to be happy. After millions of years, we were able to create a model which we call the standard model. As a matter of fact, it's not standard. It is based on a quantum theory corrected by a number of parameters and so on and so forth, where we can generate the world with a number of basic elements which is limited. We need 6 quarks, i.e. these particles which are a part of the protons and the neutrons, and of a certain numbers of what are called leptons, i.e. Muke, which is another electron, which is heavier. We have some elements crossing us, and a much heavier lepton called lepton tau, and then very few particles called bosons. Those exchanging forces when they interact, and this creates the world. The problem is that there are some pending issues. The quarks, they are called up, charm, top. They could have been called John, William, and Paul, but well, they have these names. They have the same features, with the exception of their mass. Their masses are completely different. So just imagine three things which are exactly the same. You can say they are like dots. And you put them closer and they appear to be identical. But on the contrary, one of them weighs 20,000 times more than another, and you cannot understand why. The only way to appreciate that is to use Higgs mechanism, i.e. a certain number of people, and Higgs the same, started conceiving that idea at the beginning of the 60s. They were then able to define a theory which was then perfected and then became the standard model. What was missing there? There are so many theories in the field of physics which are popular for some time, then the experiments disprove them. So it was necessary whether that particle existed or not. This is what we did. We had some problems. Watching the universe and the areas of it where there is nothing, there is no matter, there is no light emitted or absorbed, we saw that the things which are behind and which are more distant are, in a way, deviated as if there was a lens, a gravitational length made of a type of matter which we cannot see. We can see it only by these effects, i.e. watching how spiral galaxies rotate. We know how much mass they have, how they should rotate, and so on. But we cannot understand the correlation between their mass, their size, and their speed, as if there were some additional matter in there, in quite an amount. The amount is 6 times the matter which is the universe is made of. So our arrogance, dating back to 2,000 years ago, had provided us with a model where we can understand just 4% of the universe. Another thing that we discovered is that the universe, not only is it expanding, it is expanding at a higher speed, as if it had some pressure inside pushing it towards the outside. One would have thought that after the expansion, after a long time, the expansion would have slowed down. This is not the case. It is accelerating. If we calculate the amount of energy needed to do that, and you know the equation Lucio showed you, that energy and mass are two ways of saying the same thing, you see that that is 70% of the whole universe. 70% obscure or dark energy, 25% dark matter, 4% is what composes us, the stars and the light. We should not be contented with that. A number of answers were given. Many experts, and here we have some Nobel Prizes, not all of them connected with a standard model of particle physics of the past 50 years, and they proposed some possible solutions. Their theories are neither supersymmetry or extra dimensions or technicolor. Theoreticians are very creative. And they made experiments trying to find evidence to kill the old theories. The important thing is that the scale which can be explored by LHC is a scale where such theories and their faults have to be analyzed. Supersymmetry is a very elegant way to solve the problem of dark matter and other problems connected with Higgs boson. Per each particle, it is stated, which has a spin, a fermion. At the beginning, at the Big Bang, there was a full spin particle and vice versa. This is very elegant because the particles have a full spin, whereas matter particles have a half spin. So that indicates that there would be a symmetry between matter and forces. That would be a new level to understand how the universe was at the beginning. These are supersymmetrical particles, which were as much as the particles making us, and then they decayed. They were protected because once created, they cannot decay. When they stay here in the universe, they don't interact unless for the force of gravity. That's a nice theory, but so with LHC, we recreated the original conditions of the universe to see whether we could recreate these particles and have them interact like at the beginning. Extra dimensions is another possibility. We heard about the string theory. String theory states that elementary particles are little strings vibrating, and the important thing is the vibration. The strings are very, very little. In order to square the circle and to have a stable universe, they need to have a bigger size than the one we use in the theory. In physics, 100 years ago, or 120 years ago, if you were to say, well, we'll live in a world with 4 dimensions, well, most probably you would have been arrested or put in a lunacy institute or a psychiatric hospital. As a matter of fact, we live in a 3D spatial dimension plus time. And the things work together. Is if you watch a satellite over your head and watch on that satellite and compare it 1 second of that watch with one of your second, the second on the satellite is longer than your second. So that seems to be immaterial. As a matter of fact, the space and time are made of the same thing. And this is that we can something which you use in the GPS. If you don't put the conditions for the theory, you would be out of your track every 170 seconds because of the use of corrective factors. So the relativity theory is used every day in your GPS when you go shopping. So the idea that you could live in a world which at the beginning had 10 open sizes, and then when getting cooler, many of these sizes were compacted. It is as if you were to watch a paper sheet which has 3 dimensions, but the thickness is not considered. If you want to describe an elephant by using a paper, you have to use many different planes to reconstruct the elephant. We might do the same. Maybe we are writing a theory in the wrong number of sizes. The major revolution of the past century was not that of creating equations, but writing them in a different space. This is the toy at the CERN. Lucio was one, well, he's very shy, but he is one of the persons who followed LAC, and he is one of the fathers of it. This is the, well, we have the microscope, the eyes, and the experiments. 4 are big, 3 are small. For a number of reasons, well, Italians always complain. Till last year, the 5 people in charge of the most important experiments were Italians. I am the director of research. Now we have 4. The 5th is an American called Incandela, which is a name of Italian origin. At CERN, many Italians play an important role. And I'm sure you will appreciate the number of young Italians working there who studied at Italian universities and who are employed by CERN and by other foreign institutions. Our young peoples are very, very brilliant. Let's speak about the experiments. They are exaggerations. These are objects very big. CNS is smaller. They are called compact solenoids. The weight is 3 times the Tour Eiffel. They are large cameras. 1 million channels, but they can snap 40 million pics per second. And not only that, in that second they can process the 40 million pics and they select the 500 pictures where the protons smile, because that is the important thing. This is the picture that we usually display. This is a former, it's a colleague, CNS, when it was built, the largest piece was more than 2,000 tons. And it was laid at a depth of 100 meters. Well, just think this object oscillating. The data we produce are numerous. We have to add a new system. We already wrote 30 petabytes of data. A petabyte is millions of gigabytes. And still we are not finished. If we had written them on DVDs, we would have had a stack which height would have been 4 times the Mont Blanc. So we had to invent a different system, which is an evolution of the web. Networks are so powerful today in terms of band that they are much more powerful than the internal connection of a computer. A computer is made of 3 units mainly. A CPU containing data and something which dialogues with the outside. And they are all on the same bus, which decides who speaks and who does what. Just think of a very powerful network, so you can have this PC exploded on the network. You can have 250,000 computers in the world working consistently among them on the same data set in all the different places in the world. If you Google a grid monitor, which is public, you'll see that there are about 250,000 jobs working together. We had peaks of 500,000 jobs in an instant with millions of jobs per day. Why are we doing that? This is the Higgs mechanism. I could use a wonderful equation, but that would make not you understand. I'll try to explain that to you. Years ago, a lottery was organized with a wonderful champagne bottle offered to those who would have found the best analogy with Higgs mechanism. In the whole universe, there is a scalar field. That means that at any point of the universe, at any time, you can connect or put a piece of paper with a number on that. But that value has no direction. It's like having different tags with a price. This scalar field interacts with all the things in the universe passing through this field. And depending on the strength of the interaction, particles there acquire mass. The one who won was a person saying that. Let's imagine to have a great assembly like you. So if I say now, there, at that door, the Pope appears. You, or the large majority, will surround him, and notwithstanding his slim figure, he will acquire a great mass. To come from the gate to the podium, it will take a long time because there are many people around him. If I enter the door, nobody knew me before I came here. So I come, I sit down, and I have not very much mass. It would be one of the few cases in which I don't put on weight. Anyway, the nice thing is, well, so you can say, what's Higgs particle? In order to create an object with a mass, it's not necessary to have the Pope. Someone simply would say, in 10 seconds, the Pope will get there, so everybody will stand up and go at the gate. So we are all united to move, because maybe he come on the other side. It will take a long time because you are all united together. And you are Higgs boson. Higgs boson is the interaction of the field with itself, so a part of the field which becomes a particle. This is what we are looking for, because that will confirm the existence of the mechanism. So we immediately got started when the machine was fixed. We produced not many bosons per each collision. It's like looking for a needle in 500,000 haystacks. This is what we are doing. But we have good eyes. So we are lucky because Lucio gives us a lot of haystacks. Anyway, last year we had the first clues. So we don't work digitally, so you start accumulating clues to check whether that is in line with fluctuations and so on. And then when you see that at a certain point something happens more frequently, well, you are slowly convinced that you had made the real discovery. If that is consistent, well, that consistency is demonstrated through experiments. Not long ago, we started seeing events where there were special topologies with two leptons of a certain time, two other leptons, and when you reconstructed the mass from which they had decayed, the number was about 120 GeV, and then we had high-speed photons, and so on. So on the 4th of July, we caught the headlines. What's important is to be convinced. This little peak is maybe the most important discovery in particle physics in the past 30 years. We hope to do better next year. This is important because it really crowns a gigantic effort of intellectual nature from the 60s. So that model was created. A good theory is not good because it is proved by experiments, because it resists the experiments, is not falsified. Now, we are more convinced that the theory should contain something very important, because what was foreseen has been confirmed. In order to make you understand how we grow, look at the little fluctuation, which has no statistical significance. That was the point we were 1 year ago at the Congress of the European Society of Physics. At the end of the year, we're here. Then, by recalculating, we were less optimistic. And then when we decided, we were here. That means that the likelihood that this is a real fluctuation is less than 1 out of 10 millions. In physics, when a thing has a likelihood to be false less than 1 out of some millions, well, statistically, the effect is 5 sigma, and this is considered a discovery. We performed much better because we have 2 independent experiments, and they have similar effects at the same place. Good. We are happy, but that's only the beginning. And what's next? What are the features of this particle? What are the properties? So we found something which is like a cat, walks like a cat, but we don't know whether it meows or it barks. If we discover that this is a cat who barks, we will be sure that it will not part of the standard model. The other theories which I mentioned do foresee Higgs boson with 5 of them, telling us more about the dynamic nature in which mass is generated, or it might even be something different. How can we appreciate how this is? Once we have discovered that it exists and its mass, well, the properties are predetermined. If you check the channels of decay, the frequency of decay in the channels, we will be able to appreciate whether that is in line with the standard model or not. So, in the next future, we will study the decay processes, and if they are along the green line, they are within the standard model. If they are outside, and some might be outside, but the error margin is still wide and it should be narrowed, we would have made 2 discoveries. To conclude, I'd like to talk about our community, which is an interesting one from a sociological viewpoint and also generally speaking, also in terms of philosophy. When we speak of science, well, we are a very complex community. As a matter of fact, we are one of the simplest community. We are really elementary because we share a number of principles which is very limited and which is very much shared. We cannot be part of that community if we don't accept the scientific method, which is not something created by law. It is something which is created within the story of humanity and which got stable and became a way of working. There is a relationship between the observation and the speculation. We share the same and common interest and curiosity, and we are a community which is based on 2 things at the same time, collaboration and competition. There is a new term to describe our community, which is co-opetition, because we cannot carry out research if we don't collaborate, and we cannot do that if we don't compete. Competition is both vertical and horizontal. People compete within the same group of research because they want to give their contribution. Research is fantastic. Science is fantastic because it is intrinsically not democratic. What does this mean? We can't decide who is right by vote. I mean, if we are all agreed that pressure is a vector and some say, no, this is wrong, maybe he is right. It's useless to say, let's vote. And for this very reason, because we often change the paradigm, that should be performed with the most democratic tools. We should give every person who has the right idea the opportunity to present the idea, to present and defend it in front of the peers, and to be assessed through instrumental methods. We are also those who have freedom of expression. We are not politicized. We are different religions, ethnic groups, and so on. We are a simple community from that point of view. We are like a colony of ants. Here we are. These are the people working the Atlas project. Our community is much more present in the society than you could think. B-movies spoiled the image of a scientist in America. Usually a scientist is one with a white drape, with long hair and pretty outside of the world. Scientists are normal persons who ask big questions in a very practical way. Well, a scientist don't make discoveries every day. They do their work with passion, but routinely. sometimes we do something more. But just forget that scientists could be particularly brilliant. There is an important essay by Carlo Maria Cipolla, allegro, but not much, an essay on stupidity, stating that the number of stupids is independent from the job they do, the study they had, the race or the social class, and that is a constant. And this is true also for physics. We have an average number of stupids among us. Well, things we don't believe and which we fight is the second theory of Cipolla, stating that the quantity of intelligence in the world is a constant and the population is increasing, and this is devastating. So we try to give our contribution to increase intelligence as much as the number of people who are newborn. We are also lucky. We are searching for the next thing, and we know that for any answer we find, we open up new questions. So we are the ministers of a critical doubt. There is, as Latin goes, ubi dubium, where there is liberty. We need three things. And I'm sure you understand that very well, because you don't attend a meeting like this if you don't have an idea. I think I can echo the spirit you have. You're not convening here simply because you are paid or become famous or get rich. No, you do that because you cultivate 5% of your dream, your way to contribute in the advancement of the society. And this is the same for science. Everybody is to keep his or her 5% of dream, so they are aware that they can do little things for science, which is original. It is your own creation. And this is what motivates us. Then there are those where that 5% is 100% or 1,000%. These are the geniuses. And then there are those who think that they are gifted, but they are clinical cases. And this is another story. We need to have a system where we can encourage the ability to play in a large orchestra, spirit of solidarity, interest of others, while at the same time be very attentive and careful to understand the one who can play solo. A person who should be supported to do something more. Then, and that works very well at CERN, we need to have a mechanism to foster leadership and not guiding because of authority. I am the scientific director at CERN. In this environment, if I am a director and I am a stupid person, first I am a stupid and then I am a director. And this is a key element. What about the future? And I will conclude. It's easy to complain. The future, well, we have the crisis, and after the crisis we won't be back we were before. The only option is to go on. The world is global. We cannot stay seated. So research plays a key role to guarantee a sustainable future to us and our children. So we have to invest in that. If we have a lot of wheat seeds, I mean, you will die while waiting for the harvest. If you eat everything, you'll die of hunger the year after. You should balance the two things. the most important raw material for the future in the world is knowledge. And we cannot lose that process. We should convince politicians that emerging or newly emerged countries are investing a lot in basic research and innovation. China trains 1.3 million engineers per year and 5,000 PhDs in physics. So this is the way in which one becomes competitive. I do think that concentrating on finance, on thinking that the future lies in the futures is not a good idea. Thank you very much. Thank you.
Grazie.
Li ha entusiasmati, Li ha entusiasmati.
Quanti
Well, thank you very much for the very interesting hints that you gave us. We have to conclude. Let me tell you something which really impressed me. In order to go on, in order to find that discontinuity with a new novelty, real novelties, you said, we need virgin eyes, we need pure eyes, young eyes, where someone realizes that there is a novelty where everybody sees the usual things. You have to educate our glands. The wonderful experience which has been described bear witness to that. Lucio presented spectacular examples, and that is something which is useful to everyone. And that was quite unexpected. Nobody would have imagined that we could use certain things for the good of human beings when knowledge is used responsibly. Nobody had imagined that when a thing was discovered for the first time. I would like to quote Richard Feynman, one of the best physicists of our times, because I think that it contains very interesting ideas which had already been mentioned today. Speaking of the glands, which is not part of physicists only, but is part of every man. The same emotion, the same wonder, and the same mystery born continually any time that we consider a problem in a sufficiently deep way. To a better knowledge is accompanied a much more wonderful mystery which pushes us to go deeper and deeper. Thank you very much, and very well.
È la fine degli anni 70. Tra alcuni